Hello, we are starting a new chapter. Title of this chapter is GMM and 2SLS. So like 7 alphabets, 6 alphabets and a number look like a password. And those two methods are two most commonly used methods to estimate the instrumental variable regression models. So let me review the IV regression model. We have these assumptions, and remember we had two approaches, the instrumental variable approach or moment approach. So like the name of the approach is my choice. I named it this way. Anyhow, the first way to estimate beta 0 from this model is to use this. And the second method is to use the two-stage approach and just repeat, use the classical linear regression method twice. So this is the other way to estimate beta 0. And we are going to study this estimation problem and in a little more general framework. So in the previous chapter, we learned extremum estimator, but GMM is a little bit different. You will see why it's different. The basic idea is similar, but there are a little bit of difference in the mechanism. So we will explain and we will study what is the GMM framework and how to show its consistency and how to show its asymptotic normality and how to obtain the asymptotic variance. We will first study the generalized method moments. And like now it is a general framework. So the idea is that suppose that the assumption or the identification result implies that expected value of some function that depends on the parameter equals to 0 at the true parameter. So the true parameter is the solution to this equation. So this equation is the key equation for estimation, and we call this equation as the moment conditions or moment restrictions. Remember, moment is just another name for expectation. So the generalized method moment is based on expectation of something. So expectation of something equals to 0 at the true parameter. Of course, you have to have that theta 0 is the unique solution. So, and how can we estimate theta based on this condition? This is the main topic we are going to study in this chapter. So think about the notation. I am going to consider k-dimensional vector for the parameter. So the parameter includes k number of parameters, and the function, the moment function is m-dimensional. It is, the dimension can be different. Theta and the moment can be of different dimensions. And I am going to write g, a function g from ith observation that depends on the true parameter. And so this is a random function and it is a vector valued function. So this actually consists of m different functions. M functions make one vector, so that is the moment function. And extending the notation, we are going to use g hat n theta, so function, it is another function, which is simply the sample average of the moment function. And g0 theta is the expected value of the moment function. And capital G stands for the first derivative. First derivative, g hat and g0. So they are different, and we are going to use z estimation principle. And so that means, as you know, as I said, we are looking for the solution to this equals to 0. So we will make it equals to 0. but instead of G0, we estimate G hat and we make this guy equals to 0. So we are simply looking for the solution to this problem. This is what we would like to solve. Here I'll give you two examples, how many examples? 3 examples. The first 2 examples are the usual suspects. The classical linear regression assumptions imply this moment condition. So the moment condition is coming from the exogeneity assumption, and from the exogeneity assumption, the moment function depends on beta and ith observations. So the moment function should depend only on observations and the parameter. And like just replace epsilon with y minus x beta. Then this is k-dimensional value. So you defined, so it is a function of beta because as you change beta, the function value will change. And when you take its expectation, it equals to 0 by this. So only when beta equals to beta 0. That is the identification condition. So we'll discuss again if we have a chance. Second example is the IV regression model. When you have IV regression model, the moment conditions are from this exogeneity of the instruments. So exogeneity of the instruments provide the moment conditions you need. And then now the moment functions can be constructed in the same way. Z times epsilon, but epsilon is replaced by a function of beta, y minus x beta. And then now it's in m-dimensional moment function. Then moment function written in this way. Again, the moment function depends on observation and parameter. And the third example is a very famous example from the paper by Hansen and Singleton. Lars Hansen, he got the Nobel Prize several years ago. So this is the first example where the first example to which the GMM estimator was applied. So in their paper, what's interesting here is they are estimating utility function parameters. So in theory, from macro or microeconomics, you must have heard about the Euler Equation. So Euler Equation, so consider a dynamic optimization of a representative consumer. So the representative consumer chooses how much to consume and how much to save, and maximizes the expected discounted, the present value of the discounted utilities. So the sum of discounted utilities, right? Expectation of summation of discounted utility, conditional on the information you have. So you have to expect how the economy, whether the stock market will increase next year or not, whether there will be a financial crisis or not. So you have to take expectation based on your information. Here C is the consumption at time t, and AT is the asset you have at the beginning of time t. So the budget constraint goes like this. W is the wage, and RT is the interest rate. AT is your asset, I said. CT is the consumption. AT plus 1 is the asset you are going to you will have in the next period. So the balance of the asset. So and of course beta is the discount factor, and we assume that the utility function is a CRRA, constant relative risk aversion parameter utility function, which takes this form. So, and here the Euler equation. So, and maybe I believe you have learned it somewhere, maybe macroeconomics. the Euler equation implies that the intertemporal substitution rate. So you have to balance the marginal utility today and the expected marginal utility tomorrow, considering the interest rate and the discount rate. So as a result, the Euler equation is given by this form. So the denominator is the marginal utility today, and the numerator is the marginal utility tomorrow, and multiply the interest rate and discount factor. And they must balance. They must be expectedly 1. If tomorrow's marginal utility is higher than today's, then you have to save more. If the marginal utility today is higher, then you have to consume more. So it's a dynamic decision. Are you following? And additionally, we assume that, as I said, you need to have some information to form the expectation. So for example, you need to expect what would be the interest rate tomorrow, or what would be the available consumption, or you have to expect what is the wage next year. So all those, all the possible informations are included in a variable z. And then here, what we observe here is CT and RT. CT is the GDP, and RT is the interest rate, like treasury bill rate, so annual rate. So then based on these observations, we would like to estimate beta and gamma, the discount factor beta, and the risk aversion parameter, or the intertemporal substitution elasticity parameter gamma, right? And we are going to use this moment as the basis of that estimation. Isn't it clever? Well, so in macroeconomics, you just thought it's just one of the equations you have, but actually it is not easy to estimate, and very important clue to estimate the intertemporal, the risk aversion parameter. And by the way, it is a conditional expectation, conditional on z, but estimation based on conditional moment is not easy. That is very much difficult. So we rewrite the condition in this way. So this implies, so I believe you can show it implies this. It's like expected value of z times something equals to 0. It's like covariance between them equals to 0. 1 is subtracted here. The right-hand side variable, or right-hand side number, was subtracted here. So z, if you have utilized all the possible informations in z, then those two, the difference, the deviation, should be uncorrelated with the information. So the deviation must be coming from some unexpected information, unexpected shock, which is not included in the information z. So exactly this is the instrument we need. So this plays the role of instrument, and this part is a little more complicated form of this. So when you have linear function, you had a simple linear function here, but now instead of linear function, we have a little more complicated functional form, because the utility function is not linear and the marginal utility is not linear. And then how can we estimate beta and gamma? We can use the generalized method moments approach here. So it will be a very interesting method. Okay, so we'll talk about different issues in this method in the next video.